We just started the seminar for several weeks, and so we don't have a big group of people working on mirror symmetry locally. And so I made it online. At least in China, I try to advertise it a little bit. But normally we have about around 10 people.
Yeah, I think
so,
it might be a different.
Depending on
with the timing difference today.
There's another talk by around a big Chinese university in Zhejiang province at the same time, which is more popular, I think, because they have been running for 2 years. And so
nice.
There may be a little bit of conflicts today. All right, so it's 3, and we can get started. And so thank you everyone for joining this weekly seminar. Today I'm happy to introduce Kai. Is it called Hugtenburg or Huttenberg?
Hugtenburg, but I'll forgive you.
Hugtenburg. Yeah, sorry. And he will be talking about cyclic open-close maps and U connections and R-matrices. Thank you, Kai. You can start.
Yeah. Thanks all for joining, and thank you very much for inviting me. I'm very honored to speak here. So today I will talk about my recent work on cyclic open-closed map. On the way, I'll say something about U connections and R-matrices. Okay, this story all starts with enumerative mirror symmetry, and just to remind you what that is, in 1991, Candelas, de la Osa, Green, and Parks came up with this idea that there exist pairs of spaces, X and Y, where X is a symplectic manifold and Y a complex manifold, and they found that the Gromov-Witten invariants of X correspond to the period integrals of Y. So this is then X and Y in this case are an enumerative mirror pair. And in later years, in 1993, Morrison packaged this data into what's called a variation of Hodge structures. And then he came up with this idea that if you have a splitting of a variation of Hodge structures, then you can actually extract the enumerative invariants from there. And that was mainly in the Calabi-Yau setting. And then in 2001, Varanikov generalized this to the Fano setting. So in that case, instead of a VHS, you have a variation of semi-infinite Hodge structures, which is VSHS. And in the rest of the talk, I will call this a TP structure. But if you don't know any of these words, don't worry, I'll explain them in a minute. Then later, Kontsevich, around about the same time, Kontsevich came up with the idea of homological mirror symmetry. So he said that actually X and Y, if they're mirror, then what we should think of is that the Fukaya category of the symplectic space X agrees with the category of coherent sheaves of Y. And he at the same time conjectured that if such a homological mirror symmetry holds, then actually they're also enumeratively mirror. Their enumerative invariants agree. And what is the idea of this proof? I'll spell this out on the symplectic side, because that's the side that's most interesting for me. Well, the side I understand a tiny bit, is that if you take the Fukaya category of X, then you associate a TP structure or a VSHS to it. And the second step is that you show that this TP structure agrees with the quantum TP structure. Again, I will define both of these in a minute. And then finally, you show that this extra piece of data, this splitting, agrees with the splitting that arises on the quantum TP structure to obtain Gromov-Witten invariants. And I will say something in this talk about all three of these things. So number one is quite well established now, but I will remind you of this. For number two, this is work that was announced by Ganatra, Perutz, and Sheridan, and I proved this in a special case as well. And for number three, I will later talk about some interesting consequences of finding this correct splitting. Okay, so just to remind you, what are these TEP structures? We start out with a field of characteristics 0, and we take some algebra R over this field K. And then we take a finitely generated origin U module, and that's called E. And this is a definition by Hertling. It's TEP structures, but actually I consider formal TEP structures. The formal here means that we work like formal power series in the variable U. So the first piece of data we have is what's called a T structure, which is where there's a connection that sort of acts in the base directions. So in this case, it maps from derivations over on R, tensor E, to U inverse E. So this U inverse E means that it has a pole of order 1 at U is equal to 0. So the T structure is the connection in the base directions. Then we also have an E structure, which is a connection in the U direction. And U will also sometimes be called the equivariant parameter. This comes from some S1 action, but I won't really say anything about that. So an E structure is a connection in the U direction. This has a pole of order 2 at U is equal to 0. And finally, we need a P structure, which is a pairing from E, on E. And it has one property that we needed to satisfy, is that if we look at E tilde, which is E modulo U times E, then if we restrict the pairing to E tilde, then actually this pairing is non-degenerate. And for those people who have seen this language of VSHS before, is that a VSHS is a TP structure. But for me, the most interesting thing is this E structure. So the connection in the direction of U. And that's why I use this different terminology.
So Kyle, can I ask
Yeah.
a question? So why are these called T and E? I mean, P is for pairing, I assume.
Yeah, so P is pairing or polarization. The T structure stands for twister structure, I believe.
Twister.
It's from like some physics origins, I think. And E, I think, stands for extension.
Extension. Okay.
Yeah.
Okay, makes sense.
Yeah. So let me give some examples of this. So the first one is the quantum TEP structure. So in this case, let's just work over the complex numbers, and our base ring is going to be the Novikov field. And what's the Novikov field? Just like formal power series in Q, but with coefficients in the real numbers. And then the quantum TEP structure is just given by, you take the cohomology of X with coefficients in the Novikov field, and you join the formal parameter U. And then there's two connections. So to define the T structure, you have this connection in the direction of the Novikov parameter. And this is just given by derivation in that direction. And then you take the quantum cup product with the class of the symplectic form. I'll remind you of the cup product in a second. And for me, the most important one is this connection in the U direction. And there you take the derivative in the U direction, then you add a U to the -1 term, which is given by the grading operator mu, where mu acts on the pth cohomology by just multiplication by p minus n over 2. So it's like a shift of the grading operator. And in the U to the -2 term, you do the quantum cup product with the first Chern class. And just let me remind you of this. How is the quantum cup product defined? Is, well, you consider this moduli space of 3-pointed maps from the holomorphic maps from S2 or P1 to X, and you require that their push forward of the fundamental class lies in degree beta in the second homology of X. And this moduli space comes with 3 evaluation maps, so F evaluation at 0, at 1, and at infinity to X. And then the cup product between alpha 1 and alpha 2 is defined as like sum over all the degrees beta. And you sum with the Novikov parameter, and there's some push-pull formula. So first you take the evaluation at 0 and the evaluation at infinity, and you use those to pull back to the moduli space. And then using the evaluation at 1, you push it forward from the moduli space to X to obtain a cohomology class on X. And in some technical setups, including the one I work in, you can actually make sense of this theory in terms of differential forms. Okay, so any questions about this? Okay, and one piece of data I forgot to tell you about is that the pairing is given by the Poincare pairing, just like classical cup product and integrating. And one other note is like for experts is that you can extend this whole story to not work over the Novikov field, but instead work over sort of the Novikov field adjoin formal parameters to keep track of bulk deformations. So you obtain a TEP structure over a bigger base. Okay. The next example of a TEP structure is what is if you have an A infinity category, you can also associate a TEP structure to it. And for simplicity, let's just work with an unital A infinity algebra, because that makes the story a lot easier. So just to remind you, what are Hochschild chains on A? The Hochschild chains on A are just a direct sum of copies of A tensor, like K copies of A modulo the unit. So how I always picture them is like you have your element in A, which sort of lives at the bottom, and then the rest goes around in a circle.
Can I ask a question? Sorry.
Yep. Yeah.
Okay. You want to apply this to Fukaya categories, and then they are not always unital.
Yes. Yes.
How to deal with them?
So in general, what you have to do is you have to extend your category to like if you have a homotopy unit, then you can sort of extend your category to have an actual unit and then take cyclic chains on that, and then you show that that's the correct definition.
But there are many zero objects in the Fukaya categories, and I'm just reminding myself. Maybe I haven't learned many enough things. Is it just does the homotopy unit always exist, or?
Yeah, there's a construction of a homotopy unit in the Fukaya category.
What about zero objects?
Well, for zero objects, a homotopy unit is 0.
I see. Okay. So in this algebraic setting, you allow some units to be 0. Is it true?
Yeah, I think yeah, that's how you show that it's a 0 object. Is like you often should show that the unit is actually 0.
Okay. Yeah. Okay. That's okay. Fine.
But in the algebraic setting, in the technical setup I will work in, my A infinity algebra is actually going to be unital.
The actual, say it again. So the actual
in the technical setup I work in, there are strict units in the A infinity algebra.
Okay.
Yeah. So, but for simplicity, I'll assume this is always the case because it makes the notation a lot easier.
Okay.
Yeah, so we've defined cyclic chains on an A infinity algebra A. And then there's two differentials, small b and the cons big B operator. And reminder, like the Hochschild homology is you take the homology of cyclic chains with the small differential b. And then there's the negative cyclic homology, which is the one that will carry the TEP structure. And for this, you take cyclic chains on A and you adjoin the formal parameter u. And then you take the total differential b plus u times capital B and take the homology with respect to that. So this is automatically an R adjoin u module. This is the negative cyclic homology. And then one piece of data is that we assumed that our TEP structures were going to be free and finitely generated R-join U modules. And this is a deep conjecture by Konsevich and Soibelman, which was proved by Kaledin in the case that of Z-graded A-infinity categories, but we will work in the Z02 graded category. So this is an assumption we make that the category is that this negative cyclic homology is free and finitely generated. And how is the TEP structure built on negative cyclic homology? I won't give any definitions, but I'll give some references on where you can read up on this. Is that the T structure is the Getzler-Gauss-Manning connection, which was constructed by Getzler. And the E structure, so the connection in the U direction, was constructed by Shkliarov and Kazarkov, Konsevich, Pantev. And the P structured pairing is the higher residue pairing, and that was constructed by Shkliarov. And this is some extension of the Fukaya pairing on Hochschild homology. Okay, the next bit of structure I need to tell you about is the Fukaya category. So now I've told you how to associate to the negative cyclic homology of an A-infinity category a TEP structure, and we're going to apply this to the Fukaya category. First, I'll give a tiny bit of background on the Fukaya category. If you know all of this, I'm sorry. So in general, the Fukaya category of X is an A-infinity category, and the objects are Lagrangians in X, and the home space from L1 from two Lagrangian between two Lagrangians is given by the Floer cochain complex. And what is this? I'm going to work in a technical setup that's used by Soliman and Tukaczynski. And in that case, we can just we will work with one Lagrangian, and that is the Floer cochain complex, so the home space from a Lagrangian to itself, is just given by differential forms on L with coefficients in the Novikov ring. And how are the A-infinity operations defined? Well, you consider the moduli space of holomorphic maps from the disk to X with boundary on the Lagrangian. And again, you take care of all the degrees. And you require that these disks have k+1 boundary marked points and some interior marked points. And then again, you can look at evaluation maps. So if you have a disk with k+1 boundary marked points, then you get k+1 evaluation maps to the Lagrangian. And similarly, if you have L interior marked points, you get these evaluation maps EVI, so the interior evaluation maps, which evaluate to a point in X. And then the A-infinity operations, what do we need to define? We need to take a tuple of k differential forms on L, and we need to produce a differential form on L. And we do that using the moduli spaces with only boundary marked points. And then again, it's given by some push-pull formula. So you pull all the differential forms on L back to a differential form on the moduli space, and then you push them forward using the boundary evaluation map. And it's a theorem of Solomon and Tukaczynski in this case that this works and gives an actual A-infinity structure. And again, sort of for the experts in the audience, if you want, and one of the reasons why I use the setup by Solomon and Tukaczynski is that they actually define a bulk deformed A-infinity algebra. So we can actually bulk deform by all parameters in the homology of X. Okay, so the next goal is to relate the TEP structure on the Fukaya category to the TEP structure on quantum cohomology. And the first thing to mention there is the open-closed map, which was first constructed by Fukaya, Otto, and Ono in 2010. And this is a map that goes from the Hochschild homology of the Fukaya category to the quantum cohomology of X. And what does this look like? Well, in the setup that we use, you now take, instead of the moduli space with no interior marked points, you take the moduli space that has one interior marked point and the rest boundary marked points. And then what you do is, if you take a a cyclic chain, which is in this case just a tuple of differential forms, you again pull them back to the moduli space, but now you push them forward using the interior evaluation map. So that's a map to X. So this allows you to define a map from Hochschild chains on the Fukaya category to the cohomology of X. And what Ganatra does in 2019 is that he extends the definition of the open-closed map to a cyclic open-closed map. So that maps the negative cyclic homology of the Fukaya category to the quantum TEP structure. And a reasonable conjecture to make is that the cyclic open-closed map is indeed a morphism of TEP structures. And in 2015, Ganatra, Perutz, and Sheridan already announced work showing that the negative cyclic open-closed map is a morphism of TP structures. But they only work over the Novikov ring, so they only have this connection in the Q direction. And they don't consider the connection in the U direction, which is why I started thinking about my work.
So Kai, in what generality is this Ganatra's map defined?
Yeah, that will be in well, Ganatra defines his map in large generality. So I think it will work for a Liouville domain, but it will also work for a complex symplectic manifold. I think you need semi-positive. And also in his case, he actually maps to the symplectic cohomology. But for a compact symplectic manifold, that is the same as quantum cohomology. Okay, I see. Thank you. Yeah. But his definition is really general. Whereas like what I prove is that I work in the technical setup of Solomon Tukaczynski, which I will say in a minute what this is. And then I construct sort of a local cyclic open-closed map. So this maps the negative cyclic homology of just the A-infinity algebra associated to a single Lagrangian to the quantum TEP structure. But the effect is that I can work, that I obtain a morphism of TE structures. So I include the connection in the U direction. Mm-hmm. And the other bit that I do is that I work with all possible bulk deformations of the A-infinity algebra. So this is basically a connection in all the base directions. Okay, thank you. Yeah, so what are these technical assumptions? They are unfortunately very strict. Is that I need to assume that these moduli spaces with of disks with boundary on L are smooth orbifolds with corners, and that the boundary evaluation map is a proper submersion.
Can I ask another question?
Yeah.
So, it's I think it's very well known that I just want to know these things. So I give you an A-infinity category, then there are two ways of producing algebras or some algebraic things. One is the HH star. The other is HC minus. Can you explain them again?
Yes. So
yeah, I just want to catch up with these things.
Yeah. So sort of if you take the Hochschild chains on so that's CC star. You take the Hochschild chains, and then you have this like the Hochschild differential, which is small b.
Yeah.
And if you take the homology with respect to small b, then you obtain the Hochschild homology.
Okay.
And the way in which you obtain the cyclic homology is that you take the cyclic chains and you adjoin the formal parameter u.
Yeah.
And then you take the total differential, which is b plus u times capital B. So in some way, sort of cyclic chains form a bicomplex with the differential small b and the differential big B.
Yeah.
And you take like the total homology of that complex.
Yeah. Okay.
So, note that there, for example, is a natural map from negative cyclic homology to Hochschild homology. by setting U is equal to 0.
Yeah.
Yeah, sorry if that was confusing.
Yeah, it's okay. I'm a bit ignorant, but it's okay.
Any more questions? Okay. So what I was going to say about these technical assumptions is they are very strict. Fortunately, there are some examples where this actually holds. But for example, if you take CPN and the Clifford torus as the Lagrangian, or more generally, if you take flat varieties and products. But why do I use such technical assumptions? Which, I mean, Solomon Tukhchinsky stated you can, that like if you assume some virtual fundamental class techniques, then it should be possible to extend this setup to a much more general setting. But why I use their setup is that in work in progress, I relate the work of Solomon Tukhchinsky on open Gromov-Witten invariants to the negative cyclic open closed map. And hopefully at the end of my talk, I will have some time to say something about this. Okay, so assuming that we have shown that there is an isomorphism of TEP structures from the negative cyclic homology of the Fukaya category to the quantum TEP structure, what are some consequences? Yeah.
I'm sorry. Do you call them assumptions? Is it, do you so do you want to avoid the virtual techniques because they are difficult, they're not written up yet in the literature?
Yes, sorry, I definitely misspoke. They are not assumptions. Like virtual fundamental techniques are definitely not assumptions. They are very well established, but they're, I think, they were too ambitious for me to try to work with in this setting. Plus Solomon Tukhchinsky have a nice setup to work in.
But in any case, you're interested in at the moment, at least in this talk, you will focus on examples, and so for, if you deal with them, if you deal only with them, you will not need the big theory of virtual techniques, and so you can, the assumptions hold in your cases. Is that, am I correct?
Yeah, I mean, in the case of CPN with the Clifford torus, the assumptions hold.
Yeah.
But unfortunately, later I will say something like some consequences of if you were able to prove a generalization of the isomorphism of TEP structures.
Mm-hmm.
And unfortunately, in those cases, my theorem, the technical setup I use doesn't apply.
Oh, okay.
Yeah.
I understand. If you want to, okay. That sounds likely. I'm not that. I'm not that worried. I'm happy to assume everything, but of course, when you write a paper, then you get worried, and it's okay. Okay.
Yeah.
It's fine.
Yeah. I've written very clearly in my paper that indeed in some of the applications, my technical assumptions don't hold, which is, yeah, but the general picture is clear. So in assuming now that we're in the monotone case, which you can also think of as Fano, is in this case, you can set the Novikov parameter, Q is equal to 1. So instead of working over a Novikov ring, we work just over the complex numbers. And one thing that's known is that the Fukaya category, that it decomposes as a direct sum over some values W in C. And what are these values? They're values of the superpotential. So in Fuk sub W, that is and the objects in there are monotone Lagrangians, and their Maslov index 2 discount is this number W. And one thing that was shown by Ritter and Smith is that the open-closed map, if you apply it to the Hochschild homology of just one piece of the Fukaya category, so Fuk sub W, then the image of that lands in the quantum cohomology sub W, where this quantum cohomology sub W is the W generalized eigenspace for quantum cup product with the first term class. So this gives a relation between sort of Lagrangians with value of the superpotential W and sort of multiple quantum cup product by C1. And my question is, what is going to be the image of the negative cyclic open closed map applied to the cyclic homology of one of these pieces? So how does this sort of decomposition vary as we vary U? And remember, what was the E structure on the quantum E structure is that this connection in the U direction is the important one for this. And that was just given by like take the derivative in the U direction, then U inverse times the grading operator, and then U to the -2 times quantum cup product by C1. And one thing we can do in this case is to apply some like relatively straightforward results on differential equations, which were shown already now maybe 50 years ago, 60 years ago by Fukaya, Leveld, Turretin, and Vasov, is that it follows from their results on abstract E structures that there exists a decomposition of the quantum E structure into pieces indexed by quantum cup product by C1. But so this saying that the quantum E structure, we have a direct sum of quantum E structures sub W. And what is the property? Well, one of them is, of course, this is a sub E structure. So the connection preserves this component. And the second property they have is that we take this component modulo U times this component, then we just obtain the W generalized eigenspace for quantum cup product by C1. And what does this give us? I showed that if you assume that the negative cyclic open closed map respects E structures, which I've proven in a very special case, but I assume it holds for all cases, then you actually find that the image of the negative cyclic open closed map of the cyclic homology of this piece of the Fukaya category actually lies in this part of the decomposition by Fukaya, Leveld, and Turretin. So that answers that question. Any questions about this?
Yes. It's in this classical lemma. In general, you have to take a run-while cover, like U goes to U to the power.
Yes. So this is only like the first step in that decomposition. So what you're talking about is that is sort of the bigger Fukaya-Leveld-Turretin theorem, which is where the pieces on the right-hand side you end up with are going to be regular summands.
But
in this case, these pieces still have these pieces are still irregular, and this is just sort of their decomposition by eigenvalues. And then if you would sort of, the next step is to factor them as sort of some exponential bit times a regular bit. And for that you might need ramification.
Okay. To be honest, I haven't run it very well, but okay, but it's fine. It's okay.
Yeah.
Okay.
But no, one thing that's like maybe is that there's a conjecture that says that for quantum cohomology of a I think if you have a smooth canonical anti-canonical divisor, then this you don't need any ramification.
Mm-hmm.
But I will not say anything about this. So if that confuses people, then
it's okay. It's okay. I'm still. I have
No, please do keep asking questions. This is good. Yeah. So now I will go into a bit of a different direction, and so I've talked about sort of a consequence of what the isomorphism of step structures means, and now I'll talk about splittings and see what interesting results we can obtain from them. So remember that a splitting was necessary to obtain from a step structure some enumerative invariants. So what is a splitting? So if you just have an abstract P structure, E, then a splitting is just a linear map from E mod U times E, which I call E tilde, to E itself, which splits the natural projection from E to E tilde, just given by setting U is equal to 0. And what is this required to satisfy? It's required to respect the pairing. So if you take the pairing of alpha and beta on E tilde, then we require that the splitting just respects this pairing. And an example of this is that if you take the quantum TEP structure, then there exists a canonical splitting, which is just given, well, we have presented sort of, in this case, E tilde is just given by the quantum cohomology of X. And E is the quantum cohomology of X adjoining the formal parameter U. And we just take an element alpha in here and just map it to the element alpha, sort of times U to the power 0 in here, which is naturally a splitting, and it's easily seen to respect the pairing. And why are these splitting interesting? Is that suppose that we have two different splittings, S1 and S2, then you can just relate them via this gadget that's an R matrix. Just keeping track of what the splitting does. And what is an R matrix? So it's a power series in automorphisms of E tilde. And there's a formula you can write down on how you construct this R matrix. But the main thing to take away is if you have two splittings, you automatically obtain an R matrix. And why do I care about these R matrices? Is because they were shown to act on cohomological field theories. For example, Gromov-Witten theory. If you don't know what these words mean, don't worry. I will explain in a couple of minutes what sort of a more concrete application of what this R matrix does. But if you've seen this before, this might help. So the goal is to obtain some R matrices from the Fukaya category. So if we, in certain cases, this will not always happen, just to happen sometimes, and there are some examples I will show you, that the Fukaya category has some sort of what I call a geometric decomposition. So that's when the Fukaya category of X actually splits as a direct sum of Fukaya categories of some other spaces Y. So if Y sub I. And what happens in that case is that the TEP structure associated to the Fukaya category, sorry.
Because can I go back to
Yep.
the definition? Last page, can I go back to the definition of a splitting? I have a question. When I read papers by Galkin, Garshov, Iritani, they considered the quantum cohomology, and they solved the flat equation near the infinity point, which is a regular singularity. So you can solve the equation quite explicitly. And that gives a map like this, preserving the products. I'm not very sure. It's just non-symmetric products, and then this looks like that if you solve the equation near infinity, the regular singular point, then you get something like this. Is it true? I'm not sure.
No, but this is the question I asked when you give that talk. So basically, the E structure, the E structure does not give you a meromorphic bundle on P1, right? So it does not give you exactly what you have, because it's only a neighborhood of 0, not infinity. Extension to infinity is exactly a splitting data would give you.
Okay. Yeah. If it's quantum cohomology, then you have already the data.
You have a meromorphic connection on P1, then it works.
Yeah, but okay, you get some weak. Okay, you get some weak structure.
Yeah.
Okay. Yeah. Okay. So
Thank you very much for explaining that. And let me add to that. From the cyclic homology of the Fukaya category, you only obtain the information near U is equal to 0.
Okay.
So we don't have a formalism yet on how to obtain this near infinity.
Okay, so this is really the more general. Yeah. Okay. This is really more general. Okay. Good. Thank you.
Yeah. So back to the case when this Fukaya category has some sort of geometric decomposition. So you just have Fukaya categories of some spaces Yi. Then the isomorphism of TEP structures gives you some decomposition these EP structures of just the quantum cohomology of U will then decompose as some direct sum of quantum cohomologies of some spaces yi. Now, on the left-hand side, on the quantum cohomology, on the quantum TEP structure, of X, we already know that there exists sort of a canonical splitting, which was just given by sending an element alpha to an element alpha. So there exists a canonical splitting here. And on the right-hand side, we also have canonical splittings. And one observation that you can make is that this isomorphism phi doesn't respect these splittings in general. So the Gromov-Witten splitting on here doesn't agree with the pullback of the Gromov-Witten splittings on the right-hand side. So in total, by pulling back these splittings, is that we obtain an R matrix on the quantum cohomology of X. And why is this interesting? Is because then you can conjecture that, like, by the action on cohomological field theories, is that you can recover all the Gromov-Witten invariants of X from the Gromov-Witten invariance of the spaces yi. And you need one extra piece of data, which is that you need the genus 0 3-point invariance of X. But in the end, you will be able to recover the all genus Gromov-Witten invariance of X. Now, let me give some example of this, because I think this conjecture is rather abstract, and no one will believe me if I don't give any examples. So the first example is projective space. And in this case, if you take even dimensional projective spaces, or if you, with the recent work of Jumbo 2 and Einar Morim, you could also take odd projective spaces. But for even projective spaces, this works on the nose, is that the Fukaya category of CP2n decomposes as a direct sum of Fukaya categories of points. So in this case, the Fukaya category is really easy to understand. And because of the decomposition of quantum E structures, we then obtain an R matrix from the quantum cohomology of CP2n. And indeed, in this case, it was already shown that this R matrix recovers the all genus Gromov-Witten invariance of X from the genus 0 3-point invariance of X. Because in this case, the higher genus Gromov-Witten invariants of the point are just not interesting. So you don't need to consider those. So you only have the genus 0 and 3-point invariance of X. And this was a result by Givental and Teleman in their classification of semisimple homological field theories. And this will work more generally in that setting. So here I've only shown the case of CP2n, but in general, you can apply this when the quantum cohomology is semi-simple. But my conjecture is interesting because it will extend beyond the case of semi-simple quantum cohomology. So the example I care most about is the intersection of quadrics in CP5. So you take CP5, take two quadratic hypersurfaces, intersect them, that will give X. And in this case, just you get the eigenvalue decomposition of the Fukaya category. So that's like this Fuch sub W. We have eigenvalues -8. We have eigenvalue 0 and eigenvalue +8. And Ivan Smith proves in 2011, not quite on the nose, but that the derived category of the idempotent completion of the Fukaya category sub-0, so this summand, is isomorphic or quasi-equivalent to the idempotent completion of the Fukaya category of the genus 2 curve. So in this case, we have some hope of obtaining an R matrix. And I show that indeed, like, unfortunately, my technical assumptions don't hold in this setup, but I check directly that indeed there exists a unique isomorphism, in fact, of E structures from the quantum E structure of the intersection of quadrics to the quantum E structure of a point, the quantum E structure of a genus 2 curve, and another summand, which is the quantum E structure of a point. And this -8 here corresponds to this -8, which you need to do some twisting, but let's not worry about that. And if you assume that this isomorphism indeed also respects the P structure, which I haven't yet been able to prove, then you obtain an R matrix for the quantum cohomology of X. You will obtain that independently whether this isomorphism respects the P structure, but to check that it's actually an R matrix, you need it to respect the P structure as well. But if you assume you do that, you obtain an R matrix, and you can compute some Gromov-Witten invariants. And I've checked some low genus examples, and in that case, it does indeed seem to suggest that this R matrix will give you all higher genus Gromov-Witten invariants of the intersection of quadrics from the higher genus Gromov-Witten invariants of the genus 2 curve. So, yes. Any questions about that?
So what's known about Gromov-Witten invariance of genus 2 curve? So you mentioned it's I guess it's not semi-simple.
No, it's not semi-simple. So, like for example, quantum car product by C1 is nilpotent of order 2. And
it's also not generically semi-simple if you deform it.
That I don't know, but I would expect not. Well, actually, the quantum cohomology, like the genus 0 Gromov-Witten invariants of genus 2 curve are trivial.
Okay.
Because there are just no maps from P1 to a genus 2 curve. So no matter what bulk deformations you do, you always just end up with the cohomology of the genus 2 curve, which is not semi-simple.
Okay.
Yeah, but there are interesting higher genus invariants, like no interest in genus 1, but there are interesting genus 2 invariants.
But the point is, you're saying you don't need those invariants to recover quantum cohomology of X. You only need 3-point form.
Yeah, to recover the 3-point invariants, to recover the total, like all genus Gromov-Witten invariants of X, you do need all genus Gromov-Witten invariants of the genus 2 curve.
Okay, that I believe. But your conjecture is not that, right? Your conjecture in the previous slides is
so for this one, you need. So my conjecture is that to recover the all genus Gromov-Witten invariants of X, you need the all genus Gromov-Witten invariants of the YI.
And also,
and additionally, you need the genus 0 3-point invariants of X.
Well, okay. I thought this is YI's, but then it's X. All right. Then I actually believe a weaker version of the conjecture that you don't even need 0, 3, right? Why do you need 0, 3?
Like for example, actually maybe you're right, because in some way you only need the genus 0 3-point invariants to obtain the R matrix. But what you additionally need to do is that you need to exactly specify how the the R matrix doesn't give you an isomorphism of the topological parts of the cohomological field theory, and you need to do some tweaking with some numbers to make sure that this is actually respected. And you need the genus 0 3-point invariants for that. But maybe I can talk about this after the talk.
Yeah, sure. Thank you.
Yeah, but in the case indeed of like the even dimensional projective space, you don't need any of the sort of like this. You only need the genus 0 3-point invariants.
Okay, thank you.
Yeah. Any more questions about this? Okay, then in the last couple of minutes, let me say something about work in progress regarding open Gromov-Witten invariants. So these were defined by many people, but I will use definition by Solomon Tukaczynski. and they define genus 0 open Gromov-Witten invariants. And what are these going to be? Well, in general, this is just going to be like counts of disks with interior constraints on this disk. So it's this with boundary on the Lagrangian, and there's interior constraint along cohomology classes on X. And in what Solomon and Chikchinsky additionally do is that you can also have boundary constraints on point classes in L. Unfortunately, you would expect in more generally like any cohomology classes on L, but in that case it's points. So these are like similar to Gromov-Witten invariants. These are interesting enumerative invariants of a pair X with a Lagrangian L. And the goal is to obtain these from the Fukaya category. Similarly as how people want to obtain closed Gromov-Witten invariants from the Fukaya category. So one notion that Fukaya and that Solomon Tukachinsky construct is that they extend the quantum TE structure, there will be no pairing, using sort of something that's like open Gromov-Witten invariants. So what do? They consider the integration map from differential forms on X to the real numbers, and then they just consider the mapping cone of this of this map, and then define the relative quantum cohomology to be the cohomology of this cone complex, and you tensor it with the Novikov ring. And then what they additionally do is that they define a relative connection. So I will only consider this connection in Q direction in this case, because that will be most interesting for the application. But you can also do it for the connection in the U direction. So they define it on the relative quantum cohomology. And in this case, how is it given? Well, an element in this cone complex can be represented as a real number plus a differential form. So real number, differential form. And on the differential form part, it's just a connection that we already defined. And on the real number, it's just, well, the first bit is just given by take the derivative. And then there's an additional u to the minus 1 term, which is given by this operator q minus 1, 2. And as inputs, it takes a symplectic form and the differential form that we're acting on. And what is this q to q minus 1, 2? So this is defined using some moduli space with no boundary marked points and 2 interior marked points. And you just pull back the differential forms to this moduli space and you integrate. So intuitively, this is some count of holomorphic disks that goes through the Poincare dual of eta1 and eta2. And what is interesting is that in the case that the fundamental class of the Lagrangian vanishes in the homology of X, then this gives an extension of TE structures. Sorry, did you have a question?
Wait, but I thought this Q is an operator, but it seems you have a pairing here. This Q
well,
minus
this
1,
Q
2.
minus 1, 2, it maps. It is in some way a pairing, yes.
But
in general, it will be a pairing from L copies of differential forms on X to the ground ring.
Ah, okay. So it's this Q minus 1, 2 omega eta is a number.
Yeah, this is a number.
And that number lives inside the cone. I see the R part of the cone. Ah, okay.
Yeah,
I get it.
exactly.
Okay.
And you.
So it doesn't have
so
the
in general,
doesn't have the X part, just the R part. Okay.
Yeah. And in general, this Q minus 1, 2 is sort of, it's not a well-defined number in the sense that if you just take 2 inputs, then this Q minus 1, 2 is not going to be invariant under, for example, taking like this, like if you change them by an exact term, then you're not going to end up with the same number. So this is why you need to work with this cone complex to construct sort of this whole construct, like this whole term here is well defined.
I see.
But, yeah.
Thank you.
Yeah, but the main takeaway is in the end, you get, given a Lagrangian, you get some extension of TE structures. So you have the relative quantum cohomology, and this was the original E structure, the quantum E structure, and you just get the one-dimensional extension of it. And the idea is to mimic this on the Fukaya category, which I will call relative cyclic homology. So I will just define it for the Fukaya category, but it works more generally, is if you take some object in a category whose churn character vanishes. So in this case, I will take that to mean the class of the unit inside the negative cyclic homology. Then you can consider the map just from the base ring to negative cyclic chains, which is chains on the Fukaya category join the formal parameter U. And the map you consider is just mapping one in the ground ring to the unit. And then I define the relative negative cyclic homology to be the mapping cone. And you take the homology of that. So you get the relative cyclic homology. And one thing I proved is that you can equip the negative cyclic homology, the relative negative cyclic homology, with a TE structure. And in this case, again, you get an extension of TE structures. But it goes the other way around. And it works more generally for any A infinity category. So this is purely categorical data. So if you don't need to actually have a construction of the Fukaya category, you can just take any A infinity category, and this construction will work. And what do I conjecture is that in general, if you take the dual of the relative quantum cohomology that was constructed by Solomon Tukaczynski, so we call this the relative quantum homology structure, then there exists some relative cyclic open-closed map, such that the following diagram commutes. So the relative cyclic open-closed map will map the relative cyclic homology of the Fukaya category to the relative quantum homology E structure. And this will just be a commutative diagram. And I proved that under the same technical assumptions as before, this conjecture holds. But instead, again, you need to replace the Fukaya category just by Floer cohomology of a single Lagrangian, because that's all we have access to. And the other thing that I proved is that if we assume that this conjecture has been proved for the quintic threefold, then the Fukaya category that will actually determine the open Gromov-Witten invariants of the real locus, which were computed by Solomon, Pandey, and Walcher. So in that case, sort of just from the data of the extension of the E structures, you can obtain open Gromov-Witten invariants. In that case, it's much easier than the case of closed Gromov-Witten invariants. Yes, and let me finish there.
All right, thank you. So are there any questions? Well, I have a question. So in the theorem, the middle one that you have here, so if you just look at the left column, you don't claim these OC maps are isomorphisms, right?
No, not in the case when you replace the Fukaya category just with a single.
So the content is, the theorem is to prove this kind of compatible with the TE structure. I see.
Yeah.
I see. All right, thank you. Yeah, Lino and I, in this recent paper, we have some very similar this exact sequence that you come up with.
Okay.
This unito being exact thing, but we are completely indifferent for different reasons.
Mm-hmm.
But it looks very similar. You have this short exact sequence. Because we were considering Calabi-Yau structures compatible with unit, and then there we have some additional. Basically, we have to pair Calabi-Yau structure with unit class, and we want this to be 0, but it may not be 0. And it is exactly this kind of thing that you get.
That's really, I should definitely read about this. Thank you for pointing me to that.
Yeah. This compatible. So basically, the unitary property is kind of much more complicated than we thought. It is a surprise to us too. That you can, for example, if you have a club-Yau structure, you can make it cyclic, but not unitocyclic. So not in general. And you need the club-Yau structure to be compatible with a unit. And this kind of space may be bigger or maybe smaller depending on dimension of the club-Yau, even or odd. And then we have this kind of short exact sequence that you get.
That might be related then to a question I have been asking, is that if you just apply this construction to any A infinity category,
yeah,
I was wondering when this structure will, like if you, so now, like if you do this for the E structure, so for connection in the U direction, is when will this split? And that might be related to.
Yeah, that's right. The splitting, yeah, that's right. Yeah, exactly. We have some kind of obvious conditions for this to split. But other than that, we don't get anything, just anything. Are there other questions? Why, Yusuke, you are laughing. If you have a question, just ask. It's okay.
Maybe I have to read the paper to learn. I enjoyed, but I have to learn. I'm just ignorant. But thanks for the talk.
Okay. All right. Let's thank the speaker again. Thank you, Kyle, for the talk. Oh, Kyle. So I'll exit and talk to you later. Thank you.
Okay. Yes. Thank you very much for inviting me. If anyone has any more questions, feel free to email me. Or
it's a very nice talk. Let's keep in touch. I'll probably email you later.
Yes, I will get on reading your paper. This sounds really exciting.
Bye.